In this video, we're going to introduce the concept of a couple of things associated with a square matrix. Like we haven't done that enough of late. And those things are called eigenvalues and eigenvectors. Now, the root of each word, eigen, is German, and like loosely translated, very loosely translated, it translates to the word characteristic. So it's almost, and this sounds really strange, but these objects, these eigenvalues and eigenvectors, they actually say something about the character of a matrix. And by that I mean, so it's not like the character of a person, but more just some key fundamental properties. So understanding eigenvalues and eigenvectors, it gives you a deeper understanding of what a matrix is and what a matrix does. All right. So in order, there are lots of ways we can sort of approach eigenvalues and eigenvectors, but let's take the approach that's based on matrix multiplication, right? And that's an operation that we've done a lot of recently. So let's say we have a matrix, and I'm going to start with a 2 by 2 matrix, and let's say that matrix is 1, -1, 2, 4. And I'm going to pick a few vectors in R2. So let's say V1 is the vector, let's say 1, 1, right? And then V2, let's say that's the vector 1, -1, right? And then V3, let's say that's the vector 1, -2. So they're all, they're not the same by any means. These are not equivalent vectors, but I've only changed a couple things here and there, right? So what we're going to do is take each of these vectors, multiply them by a matrix, and then, look at what we get. So look at the product and look at the original vectors and see if we can garner any kind of pattern, any relationship between the two. All right? And we can even sketch the results too. Again, kind of visualizing what these vectors are and then what the matrix multiplication represents, right? So let's take the product A, V1. So that's 1, -1, 2, 4 times the column 1, 1. All right. Well, let's see what happens when we do this product. So doing our dot product of row 1 and our single column here, that's 1 - 1. And then second row again with our single column, so that's 2 + 4. And then we end up with the vector 0, 6, right? So for instance, let's say we sketch this, right? So this was our original V1 vector, and then this is the product of A and V1. So let's see if we can sketch these. Right, so 1, 2, 3, 4, 5, 6. And then let's say 1, 2, 3. Okay, so 1, 1, our I guess you could think of it as our initial vector or input vector. 1, 1 is this vector here, right? And again, I'll draw it starting with an initial point of at the origin, and then this is our vector V1. Now if I sketch the vector 0, 6 also with initial point at the origin, so it starts here, and then there is no change in the x, it just goes up 6 units. So 1, 2, 3, 4, 5, 6. So roughly, certainly not perfect by any means, but this is the vector A times V. Well, what can we say about this when we look at this sketch? For sure, the red vector is longer than the white vector. So there's a difference in the magnitude, and there's also a difference in the direction, right? So both things are changed as a result of multiplying by the matrix A, right? So we could just say this. So this vector, when we multiply the vector 1, 1 by our matrix here, we observe changes in the magnitude and the direction, right? So changes in the magnitude and direction, right? Okay, so what if we start with this vector 1, negative 1? So let's repeat this process. So let's do A times V2. So same matrix, just a different vector. So now 1, negative 1. Let's take a look at this. So if we do, again, our row times column, we have 1 plus 1, and then 2 minus 4. All right, so when we simplify, we get a vector 2, negative 2. Now, if we look at V2, which is 1, negative 1, and AV2, which is 2, negative 2, I think we see a direct relationship between these two. Do you notice that this vector here is simply 2 times the original? Right? So in other words, I can actually say that this is 2 times my vector 1, negative 1. If we were to sketch this, this is what we would observe. So let's do something similar. So let's say we start at the origin. So sketching the vector 1, negative 1, again with the initial point at the origin, it is going to be this vector, roughly speaking. And then, so this is our V2. And then if I sketch the vector 2, negative 2, well, it's going to look like this, basically right there, roughly. So 2, negative 2 would be this. So that's my AV2. So what do we observe here? Well, there's a change in the magnitude, but no change in the direction. It's almost like multiplying by this matrix simply doubles, right? And that's what this 2 is saying. It just doubles the magnitude of V2, right? So here we observe a change in the magnitude, right? But not the direction. All right. And then let's do one more calculation. Let's take our, let me scroll back up just a little bit so we can see it. Here's our V3. So let's do a V3. Same process, just a different starting vector. Same matrix. I'm not changing the matrix, just the vector that we're multiplying. Then we have 1, negative 2. So let's do our product again. We will have 1 plus 2. So we have that. And then we're going to have 2 minus 8. And then that gives us the vector 3, negative 6. Now look at it this way. So this 3, negative 6 is 3 times our original vector. So this is 3 times 1, negative 2. So again, we see that with this vector, which is different from our 1, negative 2, we observe a similar relationship, right? Where the output or the result of my matrix multiplication is simply a scalar multiple of the starting vector, the vector that was multiplied by my matrix, right? It's not the same constant, right? In this case, the vector was doubled. In this case, the vector is tripled, but there is still a relationship. If I sketch this one, right, so 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So if I sketch my original vector 1, negative 2, so it's roughly here. So that is V3. Then if I sketch the vector 3, negative 6, well, that is roughly down here. So again, I'll sketch that in a different color. And what we have is this. So this is AV3. Same observation, that the result of multiplying this vector by this matrix is the same as multiplying that vector by a constant. So in some sense, matrix multiplication produces the same result as scalar multiplication. So again, let's write this. So in this case, we observe a change in the magnitude, again, but not the direction. All right. So with this in mind, and again, let me, before we write down the formal definition, I also have to point out that it seems like this relationship, right, is only for some vectors because it didn't work for 1, 1, right? So what's special about the 1, negative 1? What's special about the 1, negative 2, right? Well, here is our formal definition of an eigenvector and an eigenvalue, and then we will talk a little bit more deeply about, if I just gave you the matrix, is there a way, is there a process for us to figure out what these special vectors are and maybe what the corresponding scalars are? Because it seems like if there is such a relationship, the scalars, these constants, don't have to be the same. All right? So here's our definition. So let A be an n by n matrix, right? So we need a square matrix. A number, and we're going to denote this number lambda, is called an eigenvalue, right? An eigenvalue of A, provided that there exists a non-zero vector, and we're going to call that vector V, in Rn, right, such that this fundamental equation is true. So that when I take my matrix and multiply my vector, the result is simply a constant times that vector, right? And this is the, right, so let me write this down. So every non-zero vector satisfying this equation, so if we can find these special vectors, right, that satisfies, so satisfying this equation is called an eigenvector of A corresponding to the eigenvalue lambda. Right. So corresponding to the eigenvalue that's called lambda, right? And the two together, so the vector v and the scalar lambda, those are referred to as the eigenpairs of the matrix, right? So the pair lambda and v together, right, is called an eigenpair of A. So it's like they can't work without each other, right? You know, so the V and the lambda that satisfies this equation, they go together. So I can't just pick any old scalar and any old vector. What I have to make sure, and whatever process we come up with for finding these two things, we have to think of them as pairs, right? So we call it an eigenpair, right? So now, so the question is, if I were just to give you the matrix A, how on earth could I find these two things, right? How could I find the vector and the scalar when it's just one equation, right? Well, let's take a look at this and see what we can do with this equation, right? Now remember, A is an n by n matrix, and V is an n by 1 column. Now recall, if I were to take the identity matrix and multiply an n by n matrix, either like putting the identity in front or putting the identity after, multiplying by the identity matrix would not change the matrix A, right? So we know this. And it turns out it also works for vectors. So for instance, if I put the identity matrix here and my vector v here, because the identity matrix is n by n and my column vector is n by, and v is an n by 1 column, then this product here is also going to be an n by 1 column. And in fact, it would have to be v, right? So what we're going to do, it's going to seem a little strange, but I'm going to take this equation, right? And I am going to insert the n by n identity right in front of v on the right hand side. So I'm going to take this equation. So here's my A times V, and I'm going to have my lambda still in front, and then I'm going to put the identity matrix there, and then my vector V there, right? And this is exactly the same as it is up here, right? It's like putting a coefficient of 1 in front of the variable, all right? Now, since we're going to try to solve this, one of the things that we do many times in solving equations is to bring all the unknowns to one side. Now in this case there are two unknowns, right? There's the scalar and then there's a vector. So I'm going to move everything to the left so it looks like this. So minus lambda IV, and then on this side I would have the 0 vector. So we have to remember that this is a vector now, right? Now, once I do this, now think about one of the things we use a lot when we're solving equations. We like to factor, right? So if you notice, there's a v in common now. So I'm going to factor out the v. So in parentheses, that's going to leave the vector, the matrix A, and then minus lambda times the identity matrix. That's going to be in the parentheses. And then outside the parentheses will be the vector v. And then I still have my 0 vector on this side, right? Now, in the definition, it says that the vector has to be non-zero, right? So in other words, we want to find a non-zero solution for this equation. This equation is homogeneous because we have a zero, a column of zeros on the right-hand side, right? So this is a homogeneous system, right? Now, the thing is, if this matrix that's in front, and this is a matrix, right? Because it's A minus a constant times the identity matrix. So if this matrix happens to be invertible, then all we have is the trivial solution, right? Because if our coefficient matrix is invertible, the system has a unique solution, and since it's homogeneous, the only solution it could have is the zero vector, which we don't want. We want the solution to be non-zero, right? So in order to have non-trivial solutions to this, so non-trivial solutions to this system, then this coefficient matrix, this matrix that's in front here, must be non-invertible. It can't have an inverse, right? In other words, it has to be a singular matrix, right? So in order to have non-trivial solutions to this system, A minus lambda I must be a singular matrix. What does it mean for a matrix to be singular? It doesn't have an inverse. What does it mean to not have an inverse? It means the determinant of this matrix has to be zero. So therefore, the determinant of A minus lambda I must be equal to zero. And this is a fundamental equation. This equation right here is called the characteristic equation of the matrix, right? So this equation here, this is called the characteristic, right, equation of A, right? Right. And what this equation allows me to do, if you notice, this equation now doesn't have the vector v. It only has the unknown scalar lambda. So if I could somehow figure out what this determinant is on the left-hand side, set it equal to zero, then that should, in principle, give me a way to solve for lambda, right? So we use this characteristic equation, right? So in fact, let me say it this way. The roots of the characteristic equation, those roots are in fact the eigenvalues, right, of the matrix. So at least now what we do, we have a method for finding the eigenvalues of a particular matrix. So if I give you A, then we can use this equation to find the lambdas. And then once we know lambda, we can go back to our homogeneous system and solve for the vector v, right? So and that's the two-step process. So we find the roots of this characteristic equation. Those roots are going to give me the eigenvalues. Once I know the eigenvalues, then suddenly the lambda is not unknown. The only unknown in this equation now, this homogeneous system, is going to be the v's, and I can solve for the v's, right? So let's do an example first, finding the eigenvalues of a 2 by 2 matrix, and then see if we can determine what the corresponding eigenvectors are. All right. So let's do an example, and let's see here. So example, and let's say A is again, let's start with a 2 by 2 matrix. 2, -12, 1, -5, right? Right. So let's go through step by step and set up this. Let's do the A minus lambda I first, right? And then find the determinant of that, and then set it equal to 0. So let's do it in stages. So A minus lambda I, right? Now in this case, the identity will be the 2 by 2 identity. So here is our 2, -12, 1, -5, minus lambda is the constant that we're going to try to find, and then the 2 by 2 identity is 1, 0, 0, 1, right? So let's write this. Let's do our matrix operations. So two operations to do. We have to multiply the identity matrix by lambda, and then subtract the corresponding entries. Right? Now, because of how the identity matrix is set up, when I distribute the lambda, I'm just going to now have lambdas on the main diagonal, and I'm still going to have zeros everywhere else. Right? So it's going to look like this: lambda, 0, 0, lambda. And now we can take the difference. So when we set up the A minus lambda I, we're just going to end up with our original matrix A, but then on the main diagonal, we're going to subtract lambda. So we're going to end up with 2 minus lambda, and then -12, and then 1, and then -5 minus lambda, right? So that's the coefficient matrix of this new homogeneous system. And we need this matrix to be singular. So we need to find the values of lambda that will make this, the determinant of this matrix, equal to 0. So now let's write down the determinant of this matrix. So the determinant of A minus lambda I, right? So use the formula for our 2 by 2 determinant. So take this entry, which is the quantity 2 minus lambda, and multiply this entry, which is -5 minus lambda, and then do minus the product of the -12 and the 1. So that's -12, right? Okay, so it looks like what we're going to end up here is with a polynomial. So let's go ahead and distribute the expand the product here. So we'll have -10, and then -2 lambda, and then plus 5 lambda, and then a plus lambda squared, and then a plus 12. All right. So let's write this, and it looks like it's going to be a quadratic. So let's write this quadratic in the standard form. So we'll write the lambda squared first, and then we end up with a plus 3 lambda, and then we have a -10 plus 12, so that's plus 2, right? So this, now before we set it equal to 0, this polynomial here is called the characteristic polynomial. And we usually denote it P for polynomial, and we usually use lambda as our variable. So let's make a note of that. So the polynomial P of lambda, which is equal to, in this case, lambda squared plus 3 lambda plus 2, This is called the characteristic polynomial. So everything is characteristic, right? So characteristic polynomial of our matrix A. All right. And in order to solve this eigenvalue, eigenvector problem, we have to find its roots, right? So for a 2 by 2 matrix, we end up solving a quadratic, all right? So if P of lambda is equal to 0, then let's write that down. So we have lambda squared plus 3 lambda plus 2 is equal to 0. And then we think, how can we solve this? Well, this one worked out nicely in that it is factorable. We can actually factor this. This factors as lambda plus 1 and lambda plus 2, right? So we have nice two integer values, all right? So our lambda is either equal to -1 or our lambda is equal to -2, right? So for this particular matrix, right, this 2, -12, 1, -5, these are the two special constants, either -1 or -2. Now what we would need to figure out, what are the eigenvectors that are associated with this value, and similarly, what are the eigenvectors associated with this value. All right, so what we're going to do is we're going to go back to the original. So now we're going to turn to that homogeneous system. So we have that A minus, let me write this lambda I. Remember, this is where it started, and we have our V, and then we have our zeros on this side. So now that we know the value, or the two possible values of lambda, we can plug those values right here, set up a homogeneous system, and solve for the vector, right? So let's do that. So when lambda is equal to -1, let's see what the system looks like. So again, let's write down our A. So it's 2, -12, 1, -5, and then minus -1 times the identity matrix, 1, 0, 0, 1, and then all of that times my V. Now what I'm going to do with the V, I'm going to write it as a column. I don't know what the components are, right? So I'm just going to call it V1 and V2. Right? So we have that, and then here we have the column of zeros. So I'm literally writing it now like in our matrix form. So let's simplify what I have in parentheses here. So it's going to be a 2 by 2 matrix. So we're going to end up with 2 plus 1, so that's 3, and then 12 plus 0, so, or -12 plus 0, so that's -12, and then 1 plus 0, that's 1, and then -5 plus 1, so that's -4. So here we go, right? So now here's the matrix equation, and the question is, what are the components of this vector? Well, we could even take this a step further and write this in our augmented form. So let's augment it and put everything together, right? And that's the system that we have to solve. Now, if you look closely, what's going to happen is we see now we can have a pivot by swapping our rows. So let's swap rows 1 and 2 so that we can get the 1 in this particular position, our upper left position. So if we swap those, then we have 1, -4, 0, and then 3, -12, 0. And now if I eliminate the +3, I will also eliminate the -12. If you look closely, the bottom equation is just a scalar multiple of the top equation. The bottom equation here is 3 times the top. So if I go ahead and eliminate that 3 by doing -3 times row 1 added to row 2, what do we end up with? 1, -4, 0, and then 0, 0, 0. And whenever this happens, we know it means we have a free variable, right? And in fact, this is always going to happen when we're solving this eigenvalue, eigenvector problem. Because we're saying that our coefficient matrix is invertible, then the homogeneous system, it can't have a unique solution. So it can only have infinitely many solutions, because a homogeneous linear system is never inconsistent. So we throw out inconsistency because it's homogeneous. We throw out the unique solution by making sure that our coefficient matrix does not have an inverse. That only leaves infinitely many solutions, right? So here's our free variable. So let v2 be equal to t, our parameter, and then this means that v1 is equal to 4t. So here is our vector. The first component is 4t, and the second component is t. And notice, because they have a t in common, we can actually factor out the t, and then we get the vector 4, 1. So what this is saying, not only is the vector 4, 1 an eigenvector, but any scalar multiple of 4, 1 will also be a vector, right? An eigenvector, right? So let's summarize this and say, when lambda is equal to -1, our eigenvector is anything of this form. And we're just going to choose this 4, 1 as a convenient kind of basis or representation of the eigenvectors that are associated with -1. So we're going to choose the vector 4, 1, and then we can, so then this would be the eigenpair. So the eigenpair would be the pair, here's the scalar, -1, and then here is that special vector 4, 1. It doesn't have to be 4, 1, because your t can be any real number. It's just choosing t equals 1 is a convenient choice, but any scalar multiple of 4, 1 will work. All right? So that's what it looks like when lambda is equal to 1, -1. When lambda is equal to -2, well, we have to repeat the process, right? So let's do that, see if we can find the second eigenpair. So when lambda is equal to -2, let's go back and set up that equation again. It's our a minus lambda. So it's a minus now -2 times the identity matrix times our vector v, and that's got to be equal to the 0 vector. So this ends up being 2, -12, 1, -5, plus 2 times the identity, 1, 0, 0, 1. Again, let me switch it over and write this first in the matrix form. So now v1, v2. So we're looking again now for another vector that will work. And then we have the column of zeros there. Simplify the coefficient matrix. Let's see what we have. So 2 plus 2, that's 4, and negative 12 plus 0, that's negative 12. And then 1 plus 0 is 1, and then negative 5 plus 2, that's negative 3. And our column v1, v2, and then 0, 0. Right? So now if we put this in the augmented form, we are going to see a similar relationship, right? Again, if we switch or swap rows 1 and 2, so if we do a row swap, this gives me 1, negative 3, 0, and then the 4, negative 12, 0, right? And again, if I eliminate the 4, I am going to automatically eliminate the negative 12, right? In fact, if you get to this stage and you don't end up with a free variable, it means something is wrong, because we have to get infinitely many solutions, right? And to see that, if we do negative 4 times row 1 added to row 2, 1, negative 3, 0, and then we have a 0 there, and a 0 there, and 0 there, right? So v2, in this case, is our free variable, so let v2 be equal to t, and that means v1 is 3t when I move it over. So that means the eigenvector in this case is of the form 3t and 1. I'm sorry, 3t and t, and then I can factor out the t and get 3, 1, right? So the eigenvectors that are associated with this second eigenvalue of negative 2 is any vector of this form, right? So let's write down the eigenpair in this case. So our eigenpair is the negative 2, that's my constant, and then the vector is 3, 1. Now, how could we check this? Well, what we could do, now that we know what the constant is, and now that we know what the vector is, here is how we could check this. Take our original matrix A and multiply this vector, right? And we could do it for the first pair. I'm just going to do it for the second pair. So if we take A times V, remember our original vector matrix is 2, negative 12, 1, negative 5. Take that matrix and now multiply this column. Do the same operations we started with, just to see if we can see this relationship between the matrix multiplication and what we now expect to be the scalar multiplication. All right. So now let's multiply. So we have 2 times 3, so that's 6, plus negative 12 times 1, so that's negative 12. And then 1 times 3, so that's 3. And then negative 5 times 1 is negative 5, so minus 5. And what do we end up with? We end up with negative 6 in the first component and then negative 2 in the second component. Notice now I can factor out a negative 2, which is my scalar right there, and look what we're left with. We're left with our original vector 3, 1. And that tells us that we in fact found the eigenvector that now is associated with this specific scalar, right? So the process is a little lengthy because you're finding constants and vectors, so you're solving polynomial equations as well as systems of equations. Now, the system that you solve ends up being homogeneous every time, but we still have to remember how to handle our free variables. All right. So in the next video, we'll work through a couple more examples and then discuss some properties that will make it a little bit easier, a little bit more streamlined, working our way through this particular process. See you then.